Salam sejahtera and a good day. This video is a special topic on data array, both in Excel and SPSS. We will then cap off this session with a small discussion on misleading statistics. Why Excel? Well, Excel is actually a software that everybody have access to. So naturally, most of us will be using Excel to gather data. So it becomes important for us to make full use of Excel and its capability to not only store data, but to clean and of course to run preliminary analysis in Excel before we analyze our data in the mainstream data analytical tools, for example, SPSS, SAS, and R software or anything of that sort. So in this case, it becomes important for us to know what Excel is capable of. Believe it or not, Excel actually has a built-in analysis tool pack, which you need to activate following the steps that has been depicted in this particular chart. It will be the same for MS Excel 2003, MS Excel 2007, 2010, 2013, and 2015. In essence, all we have to do is just to go to Microsoft Office button, click on Excel options, and as long as you can access add-ins, then you'll be able to decide what component or add-in components that you want to include and activate in Excel. In this case, in order to enable data analysis tool pack, it becomes important for you to check the option next to analysis tool pack. To gain access to this data analysis function, you then need to click on the data tab ribbon on the Excel interface. And based on that as well, we also need to know there are specific functions built into Excel that will actually allow you to do rudimentary descriptive statistics on Excel. This will be a crucial step if, let's say, we were to clean up or visualize our data prior to analysis using more mainstream software, for example, SPSS, SAS, or R. So in this case, you can see that you can build a series of values. It could be average, median, mode, minimum, maximum, using a list of commands as listed here. The crucial step that we need to remember to invoke is actually to press the equal sign in the formula bar. By pressing the equal sign, then you'll be able to invoke and key in all this formula function, entering the values according to their cell range, and then you will be able to get real-time display of the values of interest. And then again, based on the same approach, you can also perform a much more complex analytical tool, for example, t-test, and of course, Anova. And I shall be providing all this by example in the real-time classes. However, do remember that this is only accessible once you have already enabled the data analysis toolpack or options in the data tab, data ribbon tab. Another warning though, even though Excel has the capability to construct trend lines, I'm reminding everyone not to use the trendline function, which is added by Excel, because the trendline function added by Excel follows an overtly simplistic approach on how to generate a straight line. So this would be something that is detrimental if you are trying to construct a standard curve of absorbance versus substrate concentration. This is especially true for those bio-based students who need, or researchers who need to construct an absorbance curve in order to calculate substrate concentration. You can see clearly here, this is actually a curve, but the overtly simplistic Excel trendline function convert this as if, treat this as if it's actually a linear function, something that is actually totally inaccurate and totally inappropriate here. So under these circumstances, it is most appropriate that you use a dedicated trend line or maybe curve generation or curve analysis tool, for example, Curve Expert 1.4, which you can actually freely accessible from the web itself. And other than that, MS Excel's weakness will include, well, it cannot handle missing data correctly, which is actually something that SPSS excels at because of its missing function analysis. Cannot perform non-parametric statistics, even though you can actually trick Excel or reconfigure your data in order to do that. And cannot treat rank ties properly. This is actually an inherent weakness of Excel because it relied on parametric models. And of course, like what I mentioned earlier, Excel utilizes extremely simple algorithm to create linear functions. And therefore, this is suitable only for simple regression algorithms. On top of that, Excel also cannot treat zero-intercept models correctly. It had poor provisions for multicollinearity, which is important if we are trying to visualize relationships between the various factors and their dependent variables. And of course, poor calculations and estimations of residual sums. And this is actually the point where we need to transition to a more dedicated statistical analytical software. So in this case, we shall be looking at SPSS. Even though SPSS may not be the de facto, may not be the only options available for analysis, it is yet the most user-friendly due to its close proximity to Excel. The downside is that you require an active commercial license to keep on using SPSS. And this makes the options of using open source software or open source analytical tools like R very, very attractive. The only downside with analytical tools like R is that you need to be adept with some degree of programming, and you need to be able to come up with the necessary support or look for the necessary support if you are doing the necessary coding and modeling. If you are into R, that will be something that I'm encouraging everybody to go to, because R is actually a very, very powerful and a very, very flexible tool. You can customize according to what you need, and you can actually do not only data analysis, but a series of data wrangling and data processing that will allow you to fully explore the functions and potentials of data analytical tools. Now, back to SPSS. The fundamental things that you need to understand about SPSS is that it comes into tables. So you have the data view, which is actually being depicted here, and the variable view. The data view is actually where you key in the variables and their values, and there are restrictions as what is being depicted here. In general, under the data view, we treat each column of the SPSS as representing one variable or one factor, and one row as one case, one patient, or one data entry, or in this case, one experimental subject. And you need to switch between data view and variable view in order to get a grasp of your data. When we switch over to the variable views, this is actually where you can define your data. And I shall be demonstrating more in real-time classes as we interact in the class later. But in short, it allows you to define the name of the variables, the types of the variables, the definitions of how many decimals they're going to deal with, the labels, which will be very crucial in data analysis, and of course, other attributes to your variables, which makes working with data easier in SPSS. And bear in mind, SPSS also allows you to convert all these data metrics or data array into any other format of your fancy. For example, you can convert SPSS to SAS format, or maybe even reduce it to text format that you can fit later to R softwares. And of course, how you array all this data is actually important because it very much depends on experimental designs. And this is actually the emphasis of the topic that we're going to talk about today in this particular session. This experiment design not only determine how data is being arrayed, but also how certain values are being tabulated and conclusions or results being derived based on your analysis. So it is often advisable for you to organize your data sets according to recognized data array in SPSS, which we shall be looking at in the subsequent chapters. So SPSS here, or rather going through several name changes, which may include SPSS, PASW, or IBM SPSS and above, they operates in the same manner as if you are familiar with MS Excel, SAS, Minitab, and so on and so forth. So what we'll be doing is that we will be going through a series of data array that are common to data analysis, which you may be using throughout this particular course. Without further ado, let's start with the first types of design. Now, in this case, we will be looking at paired t-test. Paired t-test is actually analysis whereby we'll be comparing two values that are having the same variance or intricately linked to each other. It could be a data before and after intervention, like what is being depicted here. So you can see that this data is coming from serum, is actually depicting serum cholesterol levels from 24 nurses, which were given dietary treatments, and the values were measured before and after the dietary intervention. So you can see each pair will have one value before and one value after. In this case, it is common for us to key in the data as what we normally do in Excel by keying in the data of the subject and then the values before and values after. And then we can repeat the whole thing for the next 23 nurses in order to make up 24 subjects, which is actually being depicted in this particular slide. And in order to analyze this, when we need to convert this or transfer this to SPSS, even though we can also perform the same analysis in Excel if we already enabled the data analysis function. As you can see, the data matrix or data array is largely identical. Okay, largely identical. The only thing is that the way that the data is being analyzed will be slightly different. On the other hand, if you are running another type of t-test or independent t-test whereby the two population or the two values are not related to each other, for example, you could be dealing with one population here in Serdang and another population in another locality, say for example in Kajang, which are non-interfering to each other, then you need a design known as independent t-test design. So in this case, you can see an experiment was done to examine the effects of drug A on liver metabolite versus untreated subjects in rats. So you have 20 subjects in both groups, and this is actually how the data is being depicted. So the data matrix is being depicted this way. As you can see, in SPSS, one column is depicting one factor or one variable. So it becomes important for us to use one column to define grouping and another column to define their respective values. As you can see that you cannot key in as per the data that you have visualized in paired t-test because the computer or the analytical protocol will treat this as a paired t-test analysis, which is actually founded upon very, very different assumptions. One of them being equal variance. Independent t-test will allow some degree of variation from equality of variance. And this is actually how it's being depicted. So obviously, if you are keying in your data in Excel and then later analyzing your data in SPSS, this may include you or to rearrange our data. And every time you are rearranging a data, there is actually a potential or risk of data entry error or maybe data cleaning error. So in this case, it becomes important for you to ensure, plan ahead, and anticipate what type of analysis they're going to perform, what type of design you're going to perform, and go for the appropriate data matrix and data array so that you will minimize your propensity to edit them later in your research. Now, to make things more interesting, what happens if you have three groups? So in the prior example, you have two independent groups that are being analyzed using the t-test model. Independent t-test model to be precise. Here, if you're analyzing more than two groups, then you should be using the one-way analysis of variance model. The approach will be the same. All you have to do is just add a third group. But bear in mind here, since this is actually a one-way ANOVA, meaning that you are investigating an effects of one factor against the cholesterol levels, then it is important for us to determine and how to key in these effects appropriately. So in this case, we reserve or allocate one column for the treatment allocation and the other column for the cholesterol values. So in this case, what you have is that you have untreated controls followed by drug A and then drug B. And obviously, this is very different from how you would normally key in Excel, because in Excel, you would typically key them in side by side. As you can see later, that actually denotes another experiment design. And therefore, like what I mentioned earlier, it is important for us to know the data array or how data is actually being arranged prior to analysis using a statistical software. To make things more complicated, if you are investigating two factors, as in this case here, whereby you have treatment groups, and these treatment groups, we know that they are differing in terms of magnitude effects according to age of the animals. In this case, you end up with a 3x2 blocks. That means 3 rows by 2 column blocks, organized into 6 blocks here. And within each block, you have 6 individuals. So how do you key this into the SPSS? Well, this is actually how you do it. Just remember, in SPSS, one column means one factor. And in this case, since this is actually a two-way ANOVA, obviously you have two factors, namely the age, which is actually young and old, and the treatment factors. So in this case, we just need to define what will be the sub-levels, what will be the levels within a factor. In this case, if your factor is actually the drug types, then the levels will be untreated control, drug A and drug B. And conversely, if your factor is actually age, your levels will be young animal and old animal. In this case, depicted by young rat and old rat, because there are only two levels. And this will actually allow you to key in individual values represented within each of these 6 blocks. Notice there are 10 animals within this block control, young animal, group A, young animal, and so on and so forth. And they are clearly being depicted here. First, keying in young, and then followed by the old animals. Well, apart from handling two factors, ANOVA can also be capable of a much more complex analysis. In this case, we are looking at repeated measure ANOVA or multiple ANOVA in this case. This is actually a design whereby you could be taking a reading that are related to each other repeatedly over time. For example, you could be measuring the blood glucose levels of a rat before your experiment, 5 minutes after your experiments, 10 minutes after your experiments, 1 hour after your experiments, and so on and so forth. So this is actually aptly named as repeated measure ANOVA. The arrangement will be more or less similar. The arrangement and logic will be more or less similar to the two-way ANOVA, in the fact that you will also be dealing with multiple factors in this case. So look at this example. A veterinary anesthetist would like to investigate the effects of abnormal lung morphologies on lung perfusion in large dogs. He chose to measure expired CO2 content using a method known as end-tidal CO2 upon induction at 0 minutes, 10 minutes, and then at 20 minutes, and contrasting them over two groups of dogs, meaning normal dogs and dogs with abnormal lungs. So in this case, it's clear that we have a factor of normal and abnormal lungs. And then again, you also have a factor that is being repeatedly measured and due to the presence of time in this case. So you can see these 8 animals are measured at 0 minute, again at 10 minutes, and again at 20 minutes. And one unique point about repeated measure ANOVA is that this is the same subject that is going to be measured within the same series over time. And if we started low, with a lower value, the chances of this lower value happening in the second measurement will be there, because these are the same subjects you are dealing with. Because you could be dealing with one animal with bad lung, and then at 0 minutes, the lung still bad. At 10 minutes, chances are, of course, the lungs are still bad. The only thing is that to what extent it will affect your experimental reading. So it becomes important for us to look at a few other inherent quantities that are unique to repeated measure ANOVA. For example, multicollinearity and few other indicators. So how would you key in this data? This is actually where things becomes much more familiar to you. If you were to use this technique, this data array whereby you have normal lungs and abnormal lungs indicated on the first column, and the values measured at 0 minute, 10 minutes, and 20 minutes indicated in the separate column. Then this is actually depicting a repeated measure ANOVA. Not only that, in SPSS, you will then have to define the sub-factor, the within subject factor names. Okay, and within subject factors, then you have to define a further number of levels. Number of levels in this case simply tell you how many times these particular measurements are made. In this case, your level will be 0 minute, 10 minute, and 20 minutes. As you can see here, we are employing 3 columns. So slightly different from what we have done for two-way ANOVA. You are actually dealing with a series of factors here, but the factors are organized in different columns. If you notice, in the two-way ANOVA, they are stacked upon each other, but in a repeated measure ANOVA, they are arrayed next to each other because it depicts the same values being measured repeatedly across time for the same subjects. So these are all important aspects that you need to know in order to key in the data before you can even prepare the data for cleaning and analysis. So it makes sense for us to understand what will be the appropriate data array for each of the design. Last but not least, let's look at the data entry for a 2x2 chi-square test, a non-parametric test. So this is actually a unique test whereby you can actually test the association between two factors. Now, in this case, why don't we look at the example of a test of the association to determine whether ice cream was the cause of diarrhea among party guests. So how do you look at it? So of course, you need to have a group of determine a group of guests that eat or do not eat ice cream, and then plot them against the frequency of diarrhea among those guests. So obviously, if let's say ice cream contributed to diarrhea, the cell whereby the guest ate ice cream and having diarrhea will be of the highest frequency, and likewise, those who did not eat ice cream and did not have diarrhea will have the highest frequency. If let's say the ice cream does not contribute to the diarrhea, then all these numbers will be randomly or evenly distributed. However, if the ice cream contributed to diarrhea or it bring about diarrhea, then you will see concentration of cases in the ate ice cream diarrhea cell and did not eat ice cream no diarrhea cell. So in short, this particular vertical arrangements of cells will be hosting or be observing the highest frequency. So this chi-square test will actually allow us to see how random one distribution is going to get, and whether the distribution whereby number of frequencies concentrating on certain cells is actually enough to tell us there are association between eating ice cream and diarrhea. And these will be the tools that most medical professionals will be using in order to determine risk and odds of a factor contributing to an outcome. So how do you key all this in SPSS? As usual, you need one column for one factor. And remember that we need one factor detailing the ice cream eating status and another factor telling us the outcome. In epidemiology, which we're going to public health, which you're going to encounter later, it is a convention to put the outcome of a disease as a column. So that's why diarrhea, no diarrhea will always remain as a column parameter rather than a row parameter. A row parameter is typically reserved for risk factors. So these are the kind of things that you have to understand the moment you move on to public health. Okay, public health. So in public health, the risk factors are always written in distributed across rows, whereas the outcome, clinical outcome, is always described in their respective columns. So this is actually how you would actually program the frequencies for each of these cells. By doing this, as what is being depicted on screen, and going for Wei cases, okay, Wei cases, which is actually being depicted here, Wei cases, then you should be able to arrive at this particular table, which is identical with our initial example. So what's next then? This will actually allow you to look at a risk of having diarrhea after having ice cream. as well you can see here in risk estimate. This particular table tells us, number one, the risk is real because the number of possibilities, okay, the number of the odds ratio or number of possibilities that this person, a person is going to get diarrhea range after eating ice cream range from 1.8 to 7.02, and then the odds ratio, the median odds ratio is actually around 3.6 times. So in short, in layman's term, you can just simply say that by eating ice cream, the guest has about 3.6 times more likely to get diarrhea as compared to those who did. So in short, this will actually give us a very, very accurate, a good representation of the relationship between risk, odds, and of course, the clinical outcome. This is not only applicable for health sciences, this is also applicable through maybe to other areas, for example, finance, marketing, and even engineering and other fields or disciplines of sciences.